Alright, in this video I want to share just a few more thoughts about the fundamental theorem of calculus. Okay, so let's pretend that we're going to look at some function, and it is f prime of x. And as you might be able to guess, I want to compute the area underneath the curve from A to B. But remember, this time we aren't looking at f of x, we're looking at the derivative, which is really no big deal. It's I can treat it just like an actual graph, an original function f of x. But I think that by looking at this particular example, we're going to continue to develop our intuitive understanding of why the fundamental theorem of calculus does what it does. So I'm trying to find this area from A to B of f prime of x. And I want you to think about this. This is a new thought for you. I should be able to do this by taking this distance, which is some change in x, and multiplying it by some height. And the height that I am interested in is, you can think of it this way. I've got all these height values. These are all output values. And I'm drawing some of them, but the reality is that between A and B there's more than a million of them. There's an infinite number of those heights, right? But what I want to do is I want to find the average height of all of those heights that are living in between A and B. If I find the average one, I could turn this irregular curve into a nice geometric figure called a rectangle. And wouldn't that be nice? So what I'm asking you to believe right now is that if I take the average output value, or the average value of f prime of x, I will get some constant that I could then calculate the average of. Sorry, not the average, the area. So there's a few ways to think of this. One way that you can think of it would be like this. If you picture a giant boot stomping down on this function between A and B in such a way that it would like flatten it out, the height at which it flattens out between A and B would be the average height. And that's what I'm trying to find. So I want to find the average height of f prime of x. What I'm asking then for is an average slope, right? Or an average rate of change. And we already know how to find an average rate of change. An average rate of change between 2 points is easy to calculate. If I'm looking at the function f of x, I can find the average slope by calculating the slope between the 2 points that I'm interested in. Again, I can find the average rate of change between point A and point B by calculating the slope of this line. We've done this before in this class, right? We've navigated through a number of these problems. So if this is x1, y1, and this guy is x2, y2, then I can find the average rate of change by calculating simply the slope between my 2 points. Easy peasy. So let's review. I'm trying to find the area underneath this curve. This curve is f prime of x. If I find the average height of f prime of x, and I multiply that height, which is my unknown quantity here, by this delta x, this change in x, I've got the area underneath the curve. And I also know that the average slope, because I'm looking at f prime, is y2 minus y1 all over the change in x, right? It's over x2 minus x1. So that's where I'm at. So the average height of f prime of x, which again is a fancy way of saying find the average slope, is simply a change of y over a change of x's. Now if we start with the change of x's, we've already called our x change from A to B delta x. So let's go ahead and just put that back on the bottom, and then the change in the y values is going to be f of b minus f of a. And again, this is my average rate of change, or my average slope, which is what I'm trying to find. I'm trying to find an average slope. I'm repeating myself a lot, but I'm hoping to convince you of this. I'm just afraid that repeating myself feels like a way to convince you. That's probably not true, though. Hopefully you're tracking. Let me know tomorrow in class if you aren't. Alright, so again, what this thing is my question mark. This is my average height. This is the height that I was looking for. And again, big picture here, what I'm after is the area. So I need to multiply my height, which I've just found, by my width. So let's go ahead and write that down. The area is going to equal this height multiplied by the base. And clearly, we're going to see some stuff cancel out. Delta x cancels with delta x, and so I'm left with f of b minus f of a. The area under the curve of f prime of x is f of b minus f of a. And what I'm hoping that you're noticing, and I'll tell you in case you're not, is that the relationship between this function f prime and this function f of b minus f of a is that if we're treating f prime as the original, then f is the antiderivative. I have anti-differentiated in the same way that if I start with f, I would get capital F if I were to find the area underneath the curve. So in summary, I just walked you through an argument using the average rate of change. I walked you through an argument stating that the antiderivative, or the area underneath the curve, of f prime of x from a to b is equal to f of b minus f of a, which is something that you should believe because you already have learned the mechanics of this, and the mechanics of the fundamental theorem say, take the antiderivative of your function, which the antiderivative of the derivative would be f of x, evaluated between a and b, and we do this by calculating the difference, which would be f of the top minus f of the bottom, which is what I've just shown you through a different line of reasoning. And again, what I'd like to point out is that this is the exact same thing as the version of this that you've seen before, which is that the antiderivative of f of x dx is going to equal big F of x. Again, the relationship between big F of x and little f of x is that this is the antiderivative of this, in the same way that our f of x up here was the antiderivative of f prime of x. And we would calculate this between a and b, and we'd be left with the same result. Again, all of my energies right now are going towards trying to help you gain an intuitive understanding of what this first portion of the fundamental theorem of calculus is and what it says, and most specifically, why is it that we can anti-differentiate something, and by doing that, we're calculating the area underneath the curve. So I'm hoping that by virtue of this video and the video before, you are moving down the track of furthering your understanding. And let me just say that the content in this video and the video before, mechanically speaking, you're not going to be actually executing, an argument like this. I'm not going to have you reconstruct this. This is all just to help you develop understanding. The skills that you will be required to be able to do is to actually put this fundamental theorem into practice. So that's what we're going to be practicing more together. You'll be actually anti-differentiating and evaluating your limits and finding the difference between them. So bring your questions.